Okay, we're going to finish yesterday's lesson today with the fog day today. We need to get caught up a little bit. So we're going to skip through the slides that we did yesterday and get to where we left off. Okay, we left off right here yesterday. So we said everything is fine, like grade 11 material when we're talking about flat surfaces, sorry. But when we have our forces at an angle, it changes things a little bit because it's not the entire force that is acting on that object in the left and right or up and down direction. It's a component of that force. So one example is here where we have this crate. The tension force is at an angle. So we still have our normal force going up. We have our gravity force going down. We probably have friction going to the left. But our tension force is at an angle, and that means we have to break it into components. So from where we started, we go towards where we've ended. We're going to have an FTX component, and we're going to have an FTY component of that force. Okay, another situation is when you end up on an incline. So things look a little bit different again. So again, we have some forces at angles, but we have to decide on a frame of reference. And so what I mean by that is that if you're looking at this sled, my normal force is perpendicular to my surface. I'm going to have a tension force going up the hill. I have a friction force going down the hill, but my gravity is going straight down. Okay, so these other three forces are all at right angles to each other, but the gravity force is not. Okay, so I'm going to decide, I'm going to make everything as my reference to the slope of this hill here. And so I'm going to break down my gravity force into components, starting from where I started in the middle, going towards where I've ended. This is going to be my FGY component, and this is my FGX component. The question is then, what is the angle in here? Okay, because the hill is at an angle of 6.5, but what is that angle for that component of that gravity force? I'm just going to draw you a little picture up above here. Okay, say this was 15 degrees as our slope. That would mean that this is 75, right? Because together they make a right angle. So if I'm looking up here on my hill, and this was my little toboggan, I have my normal force going perpendicular, and this is my gravity force. And here are my components to that gravity force. I'm going to see if I can highlight it here. If this angle is 75, that means that this angle here is also 75. Right, because of the Z pattern. Okay, that Z pattern makes that angle 75 as well. And if that angle is 75, then that means this angle is 15. So whatever the slope is of your hill will also be the angle that you're looking for your components. Okay, if the slope is 15 of the hill, that angle in there is 15, and it all has to do with the Z pattern. Okay, so let's do a question. So it says to move a 45 kilogram wooden crate across a wooden floor, a coefficient of friction of 0.20, the worker ties a rope onto the crate and pulls it at an angle of 15 degrees with a force of 115 newtons. We have to draw a free body diagram. We're going to resolve this applied force into its components. And then once we have that, we can figure out the F net, and then we could calculate how much time has passed using a big 5. Okay, so it says recall. If you have the free body diagram, you can then find the F net. If you have F net equals ma, you can find acceleration. If you have acceleration, you can use a big 5, and we're going to find the time. Okay, so I'm going to redraw my picture up top here. So I have my gravity force, my normal, my friction force, and then my tension force is at an angle. There's the lunch bell. Tension force or applied force, depends how you want to look at it. I'm going to call it applied force. And it's at an angle of 15 degrees. But I'm going to break that down into components. And my FAY. Okay, so now I have to figure out, for part B, I'm going to resolve that into my components. I'm going to use sine and cos. So sine of 15 would be my opposite, FAY, over 115 newtons. Okay, so FAY, 29.76. And then I'm going to do my cos, FAX over 115. Okay, so my FAX is 111.1 newtons, going to the right. So part C is where it gets a little bit trickier because we have to find out how much time elapses. We have our free body diagram. We're going to need F net so that we can find acceleration, so that we can find time. And that's going to be a little bit tricky. To find our F net, if we're looking at our forces up top, our normal force and our FAY together are equal and opposite to FG. Okay, because our object's not flying off the ground, it's not sinking into the earth. This is different than previous questions because usually the normal force and the gravity force were equal and opposite, but not anymore because of that component force. It's FAY plus FN is equal and opposite to FG. Going from left to right then, we've got a normal force and our FAX, okay, and that's what's going to make up our F net because those are the only two unbalanced forces. Okay, so F net is our, what did I label that? FN, sorry. Friction force. Okay, so our F net is our FAX and our friction force. We know FAX, but we don't know our friction force, so we're going to have to find that first using the coefficient of friction. The coefficient was 0.20. And we need to find the normal force. And this is tricky this time because it's not equal and opposite to FG, right? It's going to be FG subtract FAY would give us our FN. Okay, so we're going to have to do FG, which is mg, subtract FAY, and that will give us our FN number. So 0.20 equals FF, our mass of 45 times 9.8, and we're going to subtract FAX. Sorry, not FAX, we're going to subtract FAY. So it's 29.76. Right, that's a Y, not an X. Okay, because FG minus FAY is going to give us our FN value. So if you multiply 45 times 9.8, subtract 29.76, multiply by 0.20, you're going to get a friction force of 82.25. Okay, I'm going to go to the next slide so I have more room for the next part. We have our friction force. We can now calculate our F net. F net is equal to our FAX and our friction force. Our FAX is 111.1 to the right, so it's positive, plus our friction, 82.25, but it's negative because it's going to the left. Okay, so when I subtract those, I'm going to get 28.85 newtons. It's positive, so my F net is still going towards the right. Now that I have my F net, I can find my acceleration, and then I can find my time. My F net is equal to 28.85 newtons. F net is also equal to MA. So 28.85 divided by 45, my acceleration is 0.64111 meters per second squared going to the right. F net and A are always in the same direction. I'm not rounding yet because I'm not done the question. Now that I have my time, I have my VI was 0, my VF is 1.4, I have my acceleration, I need my time. So I'm using my big 5 equations. I'm going to use equation number 2. VF equals VI plus AT. 1.4 equals 0 plus 0.64111 T. Okay, so then I'm going to divide both sides by 0.64111, and you're going to get 2 seconds as your time. Okay, 2 sig figs, oh, it's 2.2 seconds. Okay, so a few different things to think about in that question is that your normal force was not equal and opposite to your gravity force. It was your normal force and your FAY component, which were equal to the total of the gravity force. Okay, let's do one more question. Okay, so if two people pull on an object at different angles but with an equal force, part A, which person applied the greater horizontal force to the load? So hint, if there's no measurements given in a problem, you may want to assume some. In this case, you can assume there is a force, that should say force, of 100 newtons and angles of 30 degrees and 60 degrees respectively. Okay, so we're going to do that part first. Okay, so for part A, let's draw a picture. We have an applied force that's at an angle of 30 degrees. And we have an applied force at an angle of 60 degrees, obviously not drawn to scale here. Okay, so we're going to have components to these vectors, FAX, FAY, FAX, FAY. Okay, so let's find the x component for those vectors because that's the one that's going left to right, and we want to know who applies the greater horizontal force. Okay, so cos of 30 would be my FAX and 100 newtons of force. So it would be 86.60 newtons. For my other person, cos of 60, FAX over 100. And they've got 50 newtons. Okay, so the answer for part A is the boy that applies the greater horizontal force, and that makes sense. His angle is less, so there's a bigger component that is going in the x direction. Part B said, what effect does this have on the horizontal movement of the load? The object is going to move towards the boy because he has the larger horizontal force. Part C, which person applies the greater vertical force? So then you're doing sine of 30. Right, so we're going to get 50 newtons for the boy this time. Sine of 60. $87 for the girl. And that makes sense as well, that the girl is going to have the bigger vertical force. She has a greater angle, so a bigger component of that force is going in the vertical direction. And then part D, it says, what effect does this have on frictional forces and on the vertical motion of the load? So it's going to reduce the friction. It may lift off the floor, but it's still going to move towards the boy. Okay. Yesterday, you were assigned page 76, number 3. You can now do number 2479 on page 69, and you can do number 5 on page 83. Where do you find the solutions to these if you get stuck? They are on the wiki. Okay, good luck. You need to have these done for tomorrow so that you're ready for the next lesson.